So as you see over here, when you use the four diodes, you are going to have full wave rectification. Remember, when you use one of the diodes, you are going to turn the waves into half wave rectification. But when you use the bridge rectifier, we call it bridge rectifiers, like 4 different diodes together, you are going to have a full wave rectification. That means it's going to show all a change in the circuit. Okay. So now let's start the transistors. Transistors, we have 2 types of transistors. We are going to learn about them: PNP and NPN type transistors. Okay. So a transistor has 3 layers. Okay. It has 3 layers of doped semiconductor, and it has 3 terminals. The terminals are called base, emitter, and collector. Okay. Base, emitter, and collector. Let me show you here. So here, as you see, this is called base, this is called collector, and this is called emitter. For how are you going to differentiate whether it's a PNP or NPN transistor? So you are going to check the direction of the arrow. There is an arrow over here. If the direction arrow is from base to emitter, you are going to say it is NPN transistor. Okay. If the direction of arrow from emitter to base, this time you are going to say that this is a PNP transistor. Okay. Direction of arrow from emitter to base is called PNP transistor. It's from base to emitter, it's called NPN transistor. So NPN transistor is most common. That's why we are going to learn about NPN transistor. Okay, that is the most common one. So let's first define the base, emitter, and collector. So the base is a central region is in the transistor that controls the flow of carriers. Okay, it controls the flow of the carriers. It has very less amount of charge carriers. Okay. Emitter, on the other hand, it is a quite heavily doped, containing much larger amount of donor impurity. For the NPNT types or acceptor for the PNP types, there are many free carriers available in the emitter region because it conducts the current than the adjacent region. Okay, it conducts the current. For example, let's go back to the emitter here. The emitter conducts the current where? To the base. Okay, it conducts the current to the base for the PNP transistor because it's highly doped. On the other hand, we have collector. Collector is lightly doped. It collects charge carriers ejected from the emitter. Okay, if charge carriers are sent from emitter, not taken to the emitter, the collector collect them. That's why it's called collector. It is larger in size, so that it collects more charge carriers. Okay, it whatever charge like ejected from the emitter, like sent by emitter, the collector takes them. So there are 2 essential features of the transistors. The first one, the base layer has to be extremely thin. Okay, it shouldn't be thick. It has to be extremely thin. Okay, like a hair. Okay, like a piece of hair, you can say. And the other one, the collector must be arranged around the base, so it has to be physical. It has to be in physical contact to the base, and it has to surround the base part. Why? Because collector collects the ejected charge carriers from emitter. Okay, that's why it has to be very close to the base. So transistor biasing. Remember, biasing refers to placing voltage across the terminal of a device. Okay, when we talk about biasing, that means you are applying voltage to the device. Okay, when you talk about just like a second. Okay, when you talk about biasing, that means we are applying the voltage across terminal of the device. So a device, a diode is said to be forward bias if voltage applied to it which is unable to conduct. Okay, if we call reverse bias when there is no conduction. Okay, when there is no conduction, we call it reverse bias for a diode. If there is conduction, we call it forward bias. Let me take a pen. Okay, forward bias and reverse bias. There is conduction, so conduction, forward bias. There is not conduction, reverse bias. So the base emitter is in forward bias. Okay, thus there is going to be conduction over there. So we need for conduction we need 0.6 volt potential difference. Okay, we need 0.6 volt potential difference in order to for diode to start conduction. On the other hand, the collector base junction is normally reverse bias, okay, and hence there is a depletion layer formed spreading out in either side of the junction. So when we come to the collector base part, there is going to be a depletion layer because it is reverse bias over there. So there is no conduction between collector base part, but there is conduction between base emitter part. Okay. So the arrow on the emitter of a transistor tells you the direction of the conventional current. The conventional current. Conventional current. What was the conventional current? Do you remember? Conventional current was the current which flows from positive terminal of a circuit to negative terminal. That is called conventional current. Okay. So here, let me just show you. This is NPN transistor and this is PNP transistor. Why? Because look at the direction of the arrow. It's from base to emitter, and here it's from emitter to base. Okay. So when we apply the Kirchhoff's current law, the total current entering any junction in a circuit equals the current leaving it. So that means the emitter current will be equal to the base current plus the collector current. Okay. When we add the base current plus collector currents, we are going to get the current in the emitter. Okay. And again, we need like 0.6 volt voltage in order to start talking about the currents, start talking about the conduction for that part. So despite this, there should be no current flowing from the C because there is no current flowing over here because the first junction, the one from collector to the base, is reverse bias, right? It is reverse bias. If there is reverse bias, there is not going to be conduction. But if we give more like potential difference, then there is going to be a small amount of current flowing from through collector to base. Okay, it is going to be a small current from collector to the base. Okay, yeah. So let me just erase clear. Okay, let's continue. So okay. So the characteristic of transistors, we are going to talk about again NPN transistor because it's more common one. By its characteristic, we are going to talk about how one variable affects a second one. All other variables staying constant, okay? The one of them is going to change and it's going to affect the others, and the others are going to stay constant. In most applications, the signal at the base is used to control what is received by collector, okay? So here, for example, normally a conductor has 3 terminals, but we need 4 terminals. Why? Because there should be 2 in the input part and there should be 2 in the output part, okay? So this brings us to use one of the terminals as a common one, okay? For example, if the emitter is common, if we use the emitter common for the output and input, then we are going to have this shape. So there is going to be an arrow from emitter to collector. That is going to be output part, and our input part is going to be from base to emitter. If we use common base, then the input and output part are going to be like this. Input part is going to be this part, the down part, and output part is going to be from collector to the base part. If you use the collector as a common terminal, then the input part this time is going to be between collector to the base, and the output part is going to be from collector to the emitter. Okay, as you see, these two, their inputs are like vice versa. Okay, these two. One use common emitter and common collector. Why we use them? Again, we need 4 terminals in order to talk about input and output voltage. But since we have 3 of them, we have to use one as common. Okay, that is the reason. So when we put a circuit, a common emitter, for example, in the circuit is going to be like this. Into the circuit, there is going to be resistance over here. This is going to be input part, as you see, input here, input over here, and here is going to be output part. Okay, output part. Again, we are going to need 0.6 volt in order to start talking about the current flow. So variation in collector current with increasing voltage. So when the voltage increases, again, this is going to affect the change in collector current. So the collector current also is going to increases. But here the base current must be constant, okay? The base current must held constant. Okay, when we increase the voltage through collector emitter voltage, this is going to increase the collector current, but here there is one condition only: the base current must held constant. For example, here base current when it's 0, it is about 1 milliampere for the collector current. When it's 10 milliampere, it is going to be around like 5 milliampere. When it's 20, it's going to be around 10. When it's 30, it's going to be around 15 milliampere. Okay, so this shows that base current is constant and collector current changes according to that. Okay, from the graph you can see. So when we talk about this, we have to find the current gain. Current gain, HFE, current gain over here. So we are going to use this formula. Collector current over base current will give us current gain. Okay. We have a question next. Let's solve that questions and let's continue. So the question asking us: a transistor has a gain of 200. It doesn't have any unit. Okay. If a current of 3 milliampere is sent into the base, what is the size of the collector current would you expect? So let's do the question again. The current gain will be collector current over base current. So we have current gain over here, and we have current which is coming from the base. So when we crisscross them, we are going to find this formula: collector current equal to current gain times base current. So when we do this, we are going to get around 600 milliampere, microampere actually, not milliampere, this is micro, sorry. We are going to get around 600 microampere current in the collector, okay? We have just 10 minutes, so let's continue fast. So we can use transistor as a switch and as an amplifier inside of the a circuit. What is an amplifier? Amplifier is an electronic device that can increase the power of a signal. Okay, amplifier. So when we put a transistor inside of a circuit, we can increase the power of the signal inside of the circuit. Okay, so we can use transistor as a switch, but it is not that much reliable for large current. But for small current, if I have a small current inside of the switch, we can use it because transistor really it works really fast. So for the small amount of circuit, we can use transistor as a switch. Okay, for the small amount of circuits, small amount of current circuits, we can use transistor as a switch. But if the amount of like current it gets large, that is going to make our job hard. So that's why we don't use the transistor for the large currents as a switch. Over there we have relay, that is called relay. We use the relay in order to use as a switch. Okay. So here you can see transistor circuit. Here there is base, emitter, and collector. This is a NPN type transistor, as you see. So here there is going to be current from the collector. There is going to be current from the base, and this is the resistor over here, as you see. So this when we put an amplifier over here, amplifier, as you see, amplifier over here, there is going to be also additional to capacitor over here. Okay, so when you use the amplifier as an amplifier or like transistor, this is going to help this more signal. And here there are also two capacitor can be used in order to strong up the power. Okay, so a simple amplifier with a negative feedback. Feedback means taking some of the output signal and feeding it back to the input. Okay, when you do this, there is going to be negative feedback. So negative feedback means that is as output signal rises, it is going to rise, but apportion feedback in such way when you put the inside of the input, that is going to cause a drop to the output. Okay, when you send some current to the input, this is going to cause some drop in the output. Okay, so to understand this, we are going to consider the following sequence of events. So the first one, the current in the emitter must rise to, okay? The current in the emitter must rise to in order to talk about negative feedback. The second one, the potential difference across resistant emitter resistors must rise according to Ohm's law. Okay, V equal I times R. The third one, the voltage at emitter must therefore rise further above 0 volt. If it's 0 volt, it's not, again, this process is not going to happen. It must rise above 0 volt. The fourth one, when the transistor is conducting, like any forward bias diode, the voltage at base will be about 0.6 volt. Okay, higher than that. If it's less than 0.6 volt, that is this is not going to the conduction will not happen again. It must rise above 0.6 volt. So as the voltage at emitter rises, so must that at base as well over here. So a higher voltage at B means, like here, the higher voltage here means potential difference across RB here. So the base current falls. So the base current will fall. Why? Because there is going to be more resistance. More resistance, that means less current. So therefore the collector current here, over here, will drop out. Okay, it will drop. So a voltage operated switch, I just want to pass this part actually, we don't need this part. So logic gates, let's stop here. I don't want to like talk about the logic gates here.